So yes, indeed, the first time I wrote this slide, I did write vectors on the plane, and it was like, whoa. So the meme's there, but indeed, 2 more sections to go. Vectors are probably direction and magnitude. There is something like 90% chance that you're going to have a free response question, which is the vectors problem. Like this is one of those almost take it to the bank free response questions. So very important section. Can't leave home without it. All right. So let's define the vector. You may have already encountered vector in your physics class, but there are subtle differences between vectors in science class and vectors in the math class, not by what they mean, but how they're presented. Aaron, what can I do for you?
I just have a random question. Do you have a test in this section?
There's no possible way that we're going to get a test in before the AP exam.
The AP?
Oh, I think that very well could be a... Marissa says no.
Isn't the AP? Hey, we're going to die during the AP test anyways.
I think the AP will test it.
Yeah.
Well, remember, next year is 2012. Why are we doing anything?
Exactly.
Pardon?
So, at some point, will we have a test center?
Yes.
Dang it.
All right. So, two-dimensional vectors. Now, as Evan pointed out just before we started the lecture, vectors are direction and magnitude. Okay? We are going to write our vectors in this class as an ordered pair. What we'll refer to as it being in component form. We imagine some coordinate, AB. We imagine some line going from the origin to that point AB, and we're going to call that the vector AB. On top of that, we have one other very special vector. It's called the zero vector, and that's imagining a vector going from the origin to the origin. We say that that's the one and only vector that does not have magnitude, or it has magnitude 0. We say that's the only vector that has no direction, or I've seen in other math books that it points in all directions simultaneously. You get to pick and choose what you want to call it, but it's a special kind of vector. Now, in your book, they make a special kind of notation. Whenever they refer to a vector by its components, they'll say these chevrons in here so that you don't confuse a coordinate with the vector that points to that coordinate. When they call that vector a letter, they'll make it boldface. Now, because I have a hard time writing in boldface, what we'll do is we'll just put a little arrow over the top of the vector. So when we write it out hand, it'll be a letter with a little arrow on the top. Good? All right. Now, again, we're going to use what's referred to as this component notation. In physics class, you tend to almost always write vectors in terms of simply what is their magnitude, typically in newtons. Or meters per second. And we're going to be living in the meters per second area more than in physics. And also, they typically give the direction in terms of an angle. This component form has the angle embedded into it. There is an angle at which this vector is moved from the positive x-axis, like we've been measuring angles all along. Also in physics, they typically measure angles in terms of degrees, but of course, we know better. We do. What's the point of having this really great power series minus, well, it's less shift indeed, but you can't put the 60-degree angle in those places for x and get the right answer out. But if you do put the radian equivalent of 60 degrees, pi over 3, into all those slots, you do get the right answer. Radians is the natural way of measuring an angle. because of that, exactly this ideal. So, there we go, our definition of a two-dimensional vector.
So what is the angle?
It is the angle from the positive axis, like we've been measuring angles for other trigonometric functions all along. Okay, go to the next slide, please. Hearing. It's everyone thinking. It's causing the interference with the fluorescent lights. Let's define the magnitude of the vector. We call the magnitude of the vector also the absolute value of the vector. And if we have a vector, like we had said before, that goes to location AB, its magnitude comes from going over A and going up B, which form the two sides of a right triangle. And so it's easy to see that the magnitude is going to be A squared plus B squared, the square root of that, using Pythagorean theorem. I can fix it. There we go. If you want to open the blinds, by the way, you can do that. If you want some more light. Boy, those colors kind of pop when you do that, don't they? All right. Magnitude is always positive for vectors. Okay. And again, we'll write, if we write the vector v, if we want to refer to its magnitude, we'll just put absolute value symbols around it. Most calculus books use that notation. Some put double in that way. It's a waste of time, in my opinion.
Why are you writing velocity v?
I'm saying vector, with the vector named v. We could use vectors for velocity, and we will in a second. Are we okay then? Yes? Good? Going on then. Okay, let's talk about the direction angle of a vector. First of all, I want to reiterate the fact, since vectors are only these two components, direction and magnitude, these two vectors, who have the same magnitude, who point in the same direction, we consider them the same vectors. Sort of like a congruence thing in geometry. Every vector that has the same angle and the same magnitude, no matter where they're placed, if we slide it around, they're the same vector. So, if you can imagine taking this vector here, sliding it down to the origin, and then we say, well, what direction is it going? Well, we can then measure the angle from that particular positive x-axis and find out what angle it is. How would we do that? Here we are with this 3, 4, 5 triangle, and we're interested in that angle theta. Well, let's not worry about the 5. I mean, we know it, but we don't need it. I've got an opposite side, I've got an adjacent side. That seems to me to be the tangent function. So we'll say tangent theta is equal to 4/3. And of course, what we'll do then is take the inverse tangent of both sides. And we plug that into our calculator, and we get a number out. Now, please note that after we do that, we may need to adjust for what particular quadrant we're in. The inverse tangent function will only return angle measures that are in quadrants 1 and 4, but we're always going to represent these angles as an angle between 0 and 2 pi. So you may have to adjust based on what quadrant you're in. More on that later. Questions? All right. The head minus tail rule. If we're given a vector, let's talk about the vector that runs from -3, 3, and it runs down here to the point -1, 0. Okay, that's a vector. But if we want to write it in the component notation, we use something referred to as the head minus tail rule. We find the components by taking the x component of the head, in this case -1, and subtracting it by the x component of the tail. In this case, -3. How do we find the y component of this vector? Well, we take the y component of the head, in this case 0, subtract it by the y component of the tail, in this case 3, and we end up getting 2, -3. So that vector that I just drew is totally equivalent of going over 2 and down 3 and drawing, oops, kind of crashed into the box there, that particular vector. Oops, and I forgot also to close my chevron. There we go. Chevron?
Sounds like a car.
Well, actually, it's a gas station. But actually, all it's referred to is the stripes. All right? So, given 2 coordinates, we can find the vector that goes between those coordinates. And then this will be the vector as if it was the tail was placed on the origin. Tail, head minus tail. Head minus tail. All right. So, let's do some work with some vectors. Find the magnitude and the direction angle for the vector v, which is given in component form, -1, comma, square root of 3. Might be nice if we visualize this. I'm going to go back 1. I'm going to go up root 3, which is about there. Okay, there is that vector. How might we find the magnitude of that? Well, if you think about that triangle with 1 and root 3, well, my goodness, isn't that one of our nice triangles? Isn't it the 30, 60, 90 triangle? Perhaps? No, it is. All right? So, if we remember our triangles, the 1's there, the root 3's there, the 2's there. This angle here is the 60-degree angle, or the pi over 3 angle. This angle here is the pi over 6 angle. Now, what are we interested in? We're interested in what's the angle from the positive x to get there. Pi minus, and again, this angle here is that angle there, pi minus 3, or pi over 3. Or the angle theta is 2 pi over 3. And what about the magnitude? Well, I just saw that it's one of our famous triangles, but if we wanted to, we could say the magnitude of this vector v is equal to the square root of 1 squared plus the square root of, the square root of 1 squared plus root 3 squared, which is the square root of 1 plus 4, no, 1 plus 3, which is the square root of 4, which is 2. The magnitude is 2. If we want to do that all by hand. And that's a typical thing we might do with vectors. How many people felt really well grounded from their experience in pre-calculus doing lots and lots of vector work?
Yeah.
Pretty good? Mr. Mays put you through his paces?
What vectors?
Okay. Miss Newton, did she take it up with vectors?
Mr. Brash never taught vectors.
Mr. Brash never taught vectors.
Yes, he did.
Evan doesn't remember Mr. Brash teaching vectors. Okay. And then what about
Our last
the
chapters or something?
Yes.
okay, and unnamed pre-calculus teacher class? No, okay. That's a negative, all right. Okay, moving on. Hey, let's do the opposite way. What if I give you the magnitude and the angle, and then I ask you, can you please tell me the component form of the vector? So let's draw this out because visualization may help. I go at a 40-degree angle, something like that, and I get a vector that's going off 40 degrees. And it's got a magnitude of 3. So I imagine perhaps drawing a right triangle that will help me find the components of this particular vector. Well, the x component is going to be here. See, that's an adjacent side, and 3 is a hypotenuse. I would say that adjacent over hypotenuse would probably equal to the cosine of 40 degrees. Or we could more generalize this as x is equal to 3 cosine 40 degrees. What about y? What about the y component? Y component of that vector? Probably y over 3 is equal to the sine of 40 degrees. Or y is equal to 3 sine 40. That looks pretty good. Now, one of the problems on AP Test Day is, of course, that for all things, except for perhaps vectors, you're going to be working in radians. I would like to get out of our calculator this answer without having to switch out of radian mode. I would like to do that. Right? How might I do that? This is the way. All right. So we want 3 times cosine of 40 degrees. Well, under the angle button, under apps, above apps is a thing called angle. If I do second angle, you're going to see a little itty bitty degree sign. Little itty bitty one. And if I choose that, instead of saying 3 cosine of 40 radians, it now interprets that as 3 cosine of 40 degrees. That will give me the answer out without having to switch back into degree mode. All right? So we think the x component of that vector is 2.298. And our standard is to present 3 decimal places, unless otherwise told. How about the other one? 3 sine of 40 degrees. 1.928, and we'll round it that to 3 degrees as well, or 3 decimal places as well. Were you okay with that? Really good? Maybe a trick that you didn't know? Maybe it was a trick you did know, I don't know. All right, so again, watch out for what quadrant you're in. Make sure that the answers make sense for the quadrant that you drew the vector. Now, what do we know about vectors? Well, what we always like to do in math class is do things to vectors. We like to add them, we like to multiply them, we like to subtract them, things like that. Now, there is a distinction that maybe you heard of in your physics class, maybe not, that when we're in the world of vectors, there are also numbers that are not vectors. We have to make a compare and contrast. It's kind of like when you invent something new, you need a new name for the old thing. For example, when I was growing up, we had this thing called the telephone. But if you were to look at this thing that we call the telephone, you would not call it a telephone. You would call it a dial telephone. We didn't use the word dial telephone because it was the only one we had. We didn't have this newfangled crazy thing called a touch tone phone, which later got invented.
I would call it a landline.
And now, exactly, now these things that we call telephones, later called touch tone or dial telephones, had to get a new name to compare and contrast them to cell phones, which we didn't call cell phones, we called them car phones first.
I thought they were like bag.
Because you had to plug them into your cigarette lighter to get them to work. Bag phones would be another thing that we call it.
Crackberry.
All right, so anyway, so now that we have vectors, we need a name for the kind of thing that we've been using numbers for all along. And that special name that we're going to be giving to just plain old numbers that are not in vector form, we call them scalars. For example, when we took the magnitude of a vector, that magnitude isn't a vector. It's a scalar. It's just a plain old number. So, if we have 2 vectors, and we would like to add them together, this is called vector addition. We add their x components together. plus 2. We add their y components together, 3 plus 4, and we get a brand new vector, which is 3, 7. When you add a vector with a vector, you get a vector. You may not add a vector to a scalar. That is not a supported argument between those two types of things. But you may multiply a vector by a scalar. You may take the vector 1, 3, and you may multiply it by the scalar, oh, I don't know, negative 2. Okay, why is getting negative 2 a scalar? Because it's just a plain old number. What do we mean by multiplying a scalar times a vector? It means that we'll multiply each of the components of that vector by that scalar. And we get a new vector, negative 2, negative 6. Lastly, we can subtract a vector. We can subtract two vectors. Subtracting two vectors is actually the combination of adding and multiplying. You take the second vector, you multiply it by the scalar negative 1, and then you add the two vectors together. But mostly, it acts just like you would suppose it would. The vector 1, 2 minus the vector 3, 4 results in the vector 1, the x component being 1 minus 3, and the y component being 2 minus 4, or the vector negative 2, negative 2. So, we have operations on vectors. Addition of vectors, subtraction of vectors, and scalar multiplication. Later, when you take calculus 3, you'll learn about two more kinds of multiplication, but we're not going to get into it. That's called the dot product and the cross product. But we're not going to do it right now.
Sounds scintillating.
Fascinating. All right. We have one more definition to work on. It's called the unit vector. What I like to say when I look at this unit vector is, you know what? Vectors have magnitude and direction. Sometimes I would like to, instead of thinking about that vector as the direction of that vector like an angle, sometimes I want to think of just boiling down the vector to its pure directionness. Getting rid of the magnitude. And we do that by getting what's called the unit vector. The unit vector is found by taking the original vector and dividing by its magnitude. So, if we take a vector like 1, 3, let's call that our vector v. The magnitude of vector v is the square root of 1 squared plus 3 squared, or the square root of 1 plus 9, or its magnitude is the square root of 10. If I want the unit vector of v, I would take my vector v and divide it by, try that again, I would take my vector v and I would divide it by the magnitude of v, or I take the vector 1, 3 and divide it by the square root of 10, which is just another kind of scalar multiplication. I would get the vector 1 over root 10, comma 3 over root 10. And that special vector boils down that vector to its directionness. Now why is that? Because I've gotten rid of the magnitude. The magnitude of this vector is 1. We call it the unit vector because it always, if we follow these directions, we'll get a vector with magnitude 1. Can I show that? Sure. How about I take the square root of 1 over root 10 squared plus 3 over root 10 squared. I do that, I get 1/10. Here I get 9/10. I get the square root of 10/10, which is the square root of 1, which is 1, which is what we set off for. If we have two vectors, and I take the unit vector of both of them, and I get the same vector, it means that those two vectors are going in the same direction. I've eliminated the magnitude, what's left is only direction. Two vectors that have the same unit vector are going in the same direction. And that's slide number 9.
Wait. Can you repeat that one more time?
If I have two vectors, and I find the unit vector of both of those vectors, if I get the same vector, that means the two vectors are going in the same direction. They may not look the same at the beginning, but once I take them down to their unit form, they end up, they're the same, they're going in the same direction. All right. So let's do a little bit of vector magic on these two vectors. What do we mean by 2u plus 3v? 3. How about it's 2 times what u is equal to, which is the vector 1, 3. 3 times what v is equal to, which is the vector 4, 7. This is scalar multiplication. So how about the vector negative 2, 6 plus scalar multiplication, the vector 12, comma 21. Now we're going to add the components together and I get the vector 10, 27. Vector multiplication, scalar multiplication, and vector addition. What about u minus v? What is negative 1, 3 minus 4, comma 7? Subtract the first x component by the second x component, and I get negative 5. Subtract the first y component by the second y component, I get negative 4. And there's the result of u minus v. How about the magnitude of 1/2 of u? So I'll place my vector u in there. I'll do the scalar multiplication. And I'll get negative 1/2, comma 3/2. And now let's go ahead and do our formula for magnitude. The square root of the square of negative 1/2 plus the square of 3/2. And I'm going to get the square root of 1/4 plus 9/4, the square root of 10/4, or the square root of 10 divided by 2. Well, the square root of 4 can end up being a 2. By the way, that's one way to do that problem. It ends up with these scalars, though. I could have also changed this problem into 1/2 times the magnitude of 1, negative 1, comma 3, and gotten the same answer. I think we've already done this problem, haven't we? The magnitude of 1, 3. I think it is the square root of 10. You can see that's the same answer. All right. That's enough fun with the easy stuff. I know what you're saying. Where's the calculus? We demand calculus. Well, a couple of things. Let's not look at this slide for very long. It's in your book, but it's basically saying the kinds of things that you probably would already know. You know, u plus v is v plus u. In other words, vector addition is commutative. If I add the 0 vector to a vector u, I get u. Oh, the 0 vector is the identity vector of addition. If I multiply a scalar times any vector, I get the unit vector. I think most of these things are self-evident. So let's not spend any time on this. It's in your book, but let's do a problem. Let's go on an airplane ride. So this is an example out of your book. It's funny. So they chose to use a Boeing 727. All right, Missouri.
727's good, all right.
I don't think you can copyright a number. No, I think there's a famous lawsuit. Like, for the longest time, the Intel processors had numbers. The earliest chip was the 088, then they had the 086, and then it becomes the 286, the 80286, the 08386, and 286 and 386 were just the numbers that you referred to for these particular processors. But then their competitor, AMD, started producing chips with the same numbers. Intel sued them, and someone said, you know what? You can't copyright a number. And that's when Intel started naming their chips. Not the next one would have been the 586. That's when they started using a word instead of a number. That's when they started using the word. Instead of 586, they used the word Pentium. The Pentium chips were the first 580. Would have been called the 586. But anyway, we're off track. So a Boeing airplane is flying due east at 500 miles an hour in still air. You know what? I could represent that Boeing aircraft, all rights reserved, as a vector flying due east. I could represent it as the vector 500, comma 0. Whoops. I mean, isn't that a vector that's going due east with a magnitude of 500? I could represent the wind that it's flying in, which is 70 mile an hour coming 60 degrees from the east, Mr. Meteorologist. Sorry, 60 degrees north of east. 60 degrees north of east. Kind of like this. Oh, Charlie's going to be a meteorologist. It's got wind in it. I'm trying to throw him a bone. It's like, how often do we get to talk about weather? Every day. So the magnitude of this vector is 70, and it is 60 degrees off of that due east, which of course we would know as the positive x. And now what I want to know is what happens when we take the blue vector, let's call it the u vector. What happens when we add it to the red vector? And when we do that, we end up getting a net vector which represents what happens to this plane. Oh, plane. That should be, yay, for Danny. All right. Well, it would be easiest to add these two vectors together if they were both in component form. So can we switch the blue vector from being a magnitude of 70 with 60 degrees off the positive x? Can we switch it into component form? What was that? What was that formula we had a second ago? X is the magnitude times cosine of 60 degrees. 70 times in the cosine of 60 degrees is 1 over 2. Do we not know our cosines of 60? Okay, so if you draw the triangle, it looks like this: 1, 2, root 3, and here's the 60 degrees. So adjacent over hypotenuse 1/2. All right. How about the y? The y component of that vector is 70 times the sine of 60 degrees, which is 70 times root 3 over 2. This one's easy. That's 35. I have no idea what this one is. 70, it's 70 root 3 over 2. It's 30, no, it is. I know what it is. It's 35 root 3. What is it? 35 times approximately 1.7. 60 point what?
622.
One more decimal place, please. 2. All right. So the blue vector in component form is 35, comma 60.622, and then when we add these vectors together, 35, 60.622 plus the plane vector of 500, comma 0, and our net effect is a vector of 535, comma 60.622. Now, from a geometric standpoint, there's this idea that a couple different things you could do. If you take this blue vector and you actually transpose it onto the end of this red vector, the net effect, which I'll draw in black, there's actually the representation of this vector that we just created. When you add vectors, you can sort of transpose one onto the end of the other and then draw the net vector. There's also this idea that these things form a parallelogram, and the diagonal across that parallelogram is the net vector, again with vector addition. That won't help you on the AP exam though. You're very unlikely to get something so simple. So let's go to the stuff, the calculus part. Let's go to the stuff that is going to be helpful. Okay, and that is, oftentimes we can describe a position, let's call it a particle. Because almost every single AP question that involves vectors says, a particle is located at, and then they give you this vector description of its location. So the vector describes the location. You know what the vector ends up looking a lot like? Like a parametric equation. Like a parametric function. Oh, the x position is a function of t. The y position is a function of t. So the reason why we looked at parametrics yesterday was to prepare for this very moment. All right, now it's over. Now, what happens? If position is one vector, then we should be able to find the velocity and the acceleration based on that vector. And that vector, the velocity vector, is indeed described with the letter V. And it is found by taking the x component's derivative with respect to t and the y component's derivative with respect to t. We describe the speed of that particle as the magnitude of the vector, because speed is directionless. Velocity has direction, that's why it can be written as a vector, but speed is directionless. It's the absolute value, the magnitude of the velocity vector. Likewise, the acceleration can be described as a vector. The acceleration would be the second derivative of x with respect to t, and the second derivative of y with respect to t. Lastly, the direction can be boiled down simply as the unit vector. Now, how are these problems going to show up on the AP exam? Well, typically they give you one of these three starred things, and then they make you find the rest of them. They may give you the velocity vector and a little bit more of information, and you can always take the derivative of the velocity vector in order to find the acceleration vector. If I give you the velocity vector, you can take the antiderivative and move to the position. They give you one, and you find the other ones. All right. Here is a typical direction vector. Direction, usually again denoted by r of t, is given as sine 3t and cosine 5t. It creates this really, really cool pattern. Thank you. All right. And now what does it ask to do? Can you find the velocity vector? Well, if the position vector is sine of 3t cosine of 5t, what is the velocity, change that into an arrow. What is the velocity vector? What's our plan of attack again? Let's take the derivative of each component with respect to x. The derivative of the derivative of sine is cosine. Keep the inside the same, but don't forget the chain rule, the derivative of the inside. The derivative of cosine is negative sine. Keep the inside the same, but don't forget that chain rule. So the velocity vector in this instance is 3 cosine 3t minus 5 sine 5t. What about the acceleration vector, which is a function of t? Can we read the answer off?
-9 sine 3t.
Negative 9 sine 3t. I love the fact that we get a chance to review all these really important derivatives just prior to the AP exam.
-25 cosine 5t.
Negative 25 cosine 5t. All right. Again, this is doing it, giving position, find velocity, find acceleration. But there's no reason why I couldn't start in another place and then start at the velocity and ask for position, which is a pretty typical AP problem.
Would it mean taking the integral?
It means taking the integral, and also it means that you need one more piece of information, some sort of initial condition
For the c.
for the C. Or using something like the fundamental theorem of calculus part 2.
Oh.
But I think
The f of b minus f of a.
this is this is another one where we start at a we start at a location. This is the location vector, and we need to find all these other things. Should we blow through this? Okay, let's go ahead. So we declare that the position vector is the vector 4 sine of t 2 cosine of t. What is the velocity vector going to be? Well, the derivative of 4 sine t is 4 cosine t, I think. The derivative of 2 cosine t is what? Negative 2 sine t. Okay, so there we go. There's the velocity. What about the acceleration? Acceleration. Take the derivative one more time. Negative 4 sine t, negative 2 cosine t. Second question. Find the velocity, acceleration, speed, and direction at pi over 4. So, velocity. The velocity at pi over 4. So we're going to say, what is it at that location, or at that time? Plug and chug. 4 cosine pi over 4, negative 2 sine of pi over 4, cosine of pi over 4, something like root 2 over 2. So it's 4 times root 2 over 2, comma, negative 2 times root 2 over 2, and we end up with 2 root 2, comma, negative root 2. All right, there's our velocity. Plug and chug again for the acceleration. How do we find speed? Find the magnitude of that vector. Especially if they tell you, find the speed at a particular time. Find the velocity vector at that time. And then go ahead and find its magnitude. The derivative, the square root of 2 root 2 squared plus negative root 2 squared, which is 4 times 2 is 8. Plus 2, looks like the magnitude of the velocity is root 10. The path of this of that parametric equation is indeed an ellipse with major axis 4 and minor axis 2. Let's skip D. We're running out of time. Whoa! That's a surprise. Would you please write that down in your notes real quickly? And because what I want to do, before the moment is lost us, I would like to bring up just sort of a typical AP problem, so you can kind of see how what they look like and how there's not much to them.
So here's about like the calculus.
Just derivatives.
Okay, so what I'm going to do is I'm going to choose a random years AP exam. You got the assignment written down? Whoa! I didn't mean that. I didn't mean that. So here's the 2005, just randomly chosen. I got a whole bunch of them on my hard drive. All these exams are available on the College Board website. And if we start scooting through these problems, ooh, area between the curves. Also volume of revolution in that problem. Ooh, this one, this is from the last section that we're doing tomorrow. Oh, there's a slope field problem. There's a velocity problem. Oh man, how about that? I chose one that actually does not have a vector problem.
Well, if you had a problem, you said it was in the next chapter.
Next section. Pretty close. Let's try 02. Area between the curve problem. Here we go. There's that year's vector problem. Do you notice that they give the position of something in terms of x and y? There's your vector. And then it goes and tells you the derivative of those. Oh, part A, find the slope. Wait, that's the parametric kind of thing that we did before, right? Yeah. Do you want to find the slope at time 2? Y prime divided by x prime. dy dt divided by dx dt. Find the acceleration vector of the car when the car's horizontal position is x is equal to 140. Well, geez, they gave you the components of the velocity vector, so what's the acceleration vector going to be like? Take the derivative of those. I think I could do that. I think I could say the acceleration vector in general is the derivative of the velocity vector's x component, -4 sine t, comma, the derivative of the y component, which is going to involve the product rule, first times the derivative of the second, cosine t.
Can we just distribute the sine t in there so we don't have to do that?
Yeah, that would probably be useful. Just go ahead and say it's 20 sine t minus t sine t. You're still going to end up doing a product rule.
Well, yeah, just one product.
Okay, plus cosine t. Yep, but it's in, this problem, as you see, is like, it's a parametric problem and it's got some vectors in it.
But what do you do with the x? You just plug in there?
Well, it says the x is here, but you're going to note that the variable that's in your acceleration
It's t.
is t. So what do we need to do? We're going to need to find out what t is. If x is 140, we'll plug that back into our position equation and be able to then work backward to find out what t is. So there's the finding of the acceleration vector, which is relatively easy. The finding of the value of t that corresponds with x is equal to 140, relatively easy. And then you combine those two facts together. So a typical AP problem, it's got two things going on that you got to deal with both of them.
How would you process that? Like x equals 140.
You would say 140 is equal to 10t plus 4 sine t. This is a problem 3, so it's a calculator problem. So you don't have to solve it algebraically. You could solve this using the technology. So, pretty typical problem. Couple notes here. You don't have to wait for me to start going to the College Board website and start getting some of these problems off the website. You can do 95% of the free response questions right now. We've only got one more topic. It's going to be polar coordinates. We'll do it tomorrow. But you can start looking on the website. In fact, it may be even more beneficial to look at the website and look at vector problems in the assignment that I actually gave you. In fact, I'm going to give you the option.
Huh?
You can either do the homework assignment as I laid it out, or you can go to the College Board website, download some of these free response questions that have been released, and do the vector problems from then. Either way, all right? Not only the problems up on the board are up on the website, but so are the scoring guidelines to tell you what the right answers are. Yes.
Are you gonna post the answers to the other packets?
You know, I meant to print out the solution manual, and I didn't. Tomorrow.
Okay, but like to the ones like the other packets that are on there.
All the other packets. I mean, you're talking about
The review packets.
the review packets. Those answers is a PDF on the website. It says DC review packet. There's a PDF that's got the answers already up. All right. All right. You've been a great audience. I'll tell you, let me start off the recording. apcentral.collegeboard.com. But if you just go Google, let's say 2010 AP Calculus BC exam, free response, you're going to end up on the right page.
I won't be here tomorrow, Mr. Fair.